Welcome to EQ2 of the water cycle and water insecurity as your revision guide. This is EQ2, and the question for EQ2 is what factors influence the hydrological system over short and long-term timescales? So again, this revision guide is not a replacement for lessons or learning. It's not a replacement for wider reading. It's not a replacement for independent revision. What it does do is give you some ideas of the types of things we looked at in EQ2 and the pointers from which you should take. So let's start off by looking at the types of droughts that we get in the world. There are three types of droughts mainly that we receive, and they are meteorological, agricultural, and hydrological. So a meteorological drought is to do with weather, and that is dry weather patterns dominating an area. An agricultural drought is when there's a lack of moisture in surface soil, and that helps support plant life. And so if there is a lack of moisture in surface soil, plant life is at risk. And finally then, hydrological droughts are actually when there is evidence of low water supply. So in the hydrological cycle, there may be a lowering of the amount of water storage in reservoirs, in streams, etc., and they start to dry up, and that is what a hydrological drought is. Now, these types of droughts can be caused by one specific thing in the Pacific Ocean, and that is the El Niño Southern Oscillations, or ENSOs. So, in the Pacific Ocean, between Australia and Peru, or South America, in a normal year, what you expect to find happening is as follows. We get trade winds, which are usual wind patterns, from the east in Peru to the west in Australia. What that does is it pushes warmer water to the west, towards Australia. What we get is that warmer water rising in the ocean, so we get upwelling. Evaporation takes place because of the warm water and air, and then there is rainfall and quite large storms over the Pacific Ocean. So that's a normal year in the ENSO's system. Now, in an El Nino event, which occur every 2 to 7 years, what we actually get is those trade winds we mentioned earlier from east to west weakening. Okay, so they weaken. And that means that the ocean current, the warm water current, slows. And that also means that what we get is the rainfall does not reach, let's say, the middle of the Pacific Ocean and instead stays or remains over South America. So that means that South America, Peru, for example, gets heavy bursts of rainfall, regular flooding, regular storm events, and Australia remains pretty dry. Now, the opposite almost happens with an La Nina event. And again, this takes place after an El Nino event every 7 years or so, okay? And a La Nina event is the opposite. The trade winds are actually stronger than a normal Pacific condition year. That means the ocean currents are stronger, upwelling is stronger, and the warm ocean currents move towards the west, so they move towards Australia. And that means the rainfall occurs over Australia, and therefore Australia receives more rainfall, heavy storms, flash flooding, etc. But that La Nina event will also mean that South America suffers from droughts, suffers from meteorological droughts, agricultural droughts, and hydrological droughts too. So what you've got to try and do basically is link these ENSOs to the types of droughts. So just to recap, normal Pacific conditions, you could get droughts in both South America and Australia, but you will get the generic weather for those areas. In an El Nino event, you will definitely get a drought in Australia. And in a La Nina event, the droughts will occur in South America. Now, you had two case studies to look at. I'm just going to change this because there's a slight mistake there. There we go. And those two case studies were as follows. Desertification in the Sahel. In other words, the Sahel region of Africa becoming more like a desert, and Australia. So let's go through each of those two case studies now. So this is just a roundup of the main points that you should take from these case studies in relation to rainfall, in relation to the hydrological cycle, and in relation to ENSO as well, if you think about the weather patterns. Although, of course, ENSO does not affect the Sahel as much. So, desertification is caused by changing rainfall patterns, lack of vegetation, soil erosion, and wind erosion. So that's what creates desert. In the Sahel, around 30% of the rainfall annually has fallen in recent years. So there's a 30% drop in annual rainfall in recent years. And this is because of human factors such as overpopulation and population growth, overgrazing by cattle on farms, overcultivation through crop growth, and deforestation. These all create pressure on aquifers, underground water supply, and underground storage of water. And what we've also seen is civil war in the region of the Sahel over water and resources. And that has intensified because of the fall in annual rainfall. And remember, the reason there is a 30% drop in the annual rainfall in the Sahel is because of the human factors that have been mentioned. And all of these, as we looked at in EQ1 earlier, have an impact on the amount of rainfall that can be created and therefore the amount that actually falls overall. That's just one example of an area in the world that's receiving meteorological drought, agricultural drought, hydrological drought because of rainfall patterns and human impacts as well. In terms of Australia, then, this is a contrasting case study in a way. Australia has a recurrent feature of drought in its climate. So it's used to drought, particularly in the outback in the central regions. 30% of the country is rainfall deficient, so 30% of the nation does not receive enough rainfall for the amount of population there is and to aid supply. And El Nino events worsen this. As we said earlier, El Nino actually creates more problems when it does happen. 2006 was an example of a 1 in 1,000 year event associated with long-term climate change, and that was called the Big Dry. 2006 essentially was a year where El Nino occurred, and therefore Australia received very little rainfall all year round in 2006. So that led to real problems with hydrological, agricultural droughts, and meteorological droughts. However, Australia, unlike the Sahel, has actually been able to manage their scarce resources well. And that may be linked to development. That may be linked to the fact that Australia is a highly developed nation with the capability to do so, whereas the Sahel nations in that central band of Africa are not as developed and do not have the education as individuals to be able to manage the water supply as well. So in Australia, what we've got is things like large-scale recycling of grey water and used water. We've got desalination plants that are now popping up, which means that we can desalinize seawater for human use. And we've got new conservation strategies in place to try and conserve water as much as possible. So these two case studies are really useful for answering 12 and 20 mark questions on the use of water, human factors that affect water supply and amounts, and so on. Now, we need to look at the impacts of droughts and the impacts they have on two ecosystems very briefly. And we are going to look at, as the specification asks, wetlands and forests. So, first of all, with wetlands, these make up 10% of the Earth's surface. Okay, so they're 1/10 of the Earth. These act as water stores. They recharge aquifers for us and they trap pollutants in them. So they perform an environmental good. However, drought causes less interception by plants in wetlands, less infiltration by the soil, and therefore the water table overall falls during a drought. So there is less water stored by the wetland, and that decreases the function performed by the wetland in being able to recharge aquifers, trap pollutants, and act as a water store. So essentially, what we're saying here is wetlands are an environmental good. They're an ecosystem that actually help create a better environment and climate, therefore, overall. However, when drought occurs, actually infiltration interception drops, the amount of water stored drops, and therefore those functions earlier mentioned can't be as effective as they were. In terms of their resilience, wetlands are actually quite resilient. They are really good at being able to adapt, and the plants and the soils of wetlands can adapt well to human interference. So what we need to make sure of in future is that we keep those wetlands resilient and make sure that we try to reduce the amount of drought that exists in them so that they can act to recharge our aquifers and water stores and trap pollutants. In terms of forests, we know that forests are responsible for much of the world's interception, and they're responsible for reducing flooding and reducing the overland flow of water or surface runoff because they soak up and use that water and evaporate. Transpiration takes place, etc. So they're a crucial part of the hydrological cycle. Drought increases the likelihood of fungal diseases in forest pines and threatens their survival. So, what drought does is it actually is directly threatening the forest, as what it's doing is providing the conditions for diseases to spread through forest trees and therefore threatening interception rates, threatening a rise in flooding, threatening more surface runoff, etc. In terms of forest resilient, they are also resilient, okay? But humans have had a lot of interactions with rainforests and other forests over the last 100 years because of urbanization, because of building, human interference in general, and also because of climate change and erratic weather cycles. Okay, so forests are resilient, but because of our changing nature of using landscape, they are also changing. So, what weather patterns cause flooding? What is it that actually causes flooding? There are three main things. One, intense storms with a short lag time on the hydrograph, and they're common in more mountainous areas because of relief rainfall. Two, prolonged heavy rainfall, like monsoon seasons in India or low areas of depression in the UK. And three, rapid snow melt. So, in warmer seasons, like in Alaska, we mentioned earlier, we know that snow and ice will melt. That can create an abundance of water, which causes flooding because infiltration rates are lower than the amount of water in the system. However, that's not it because there are more general physical factors that do cause flooding, and they might be things such as topography or relief, which is the shape of the land. So, low lying areas with impermeable or hard surfaces are more likely to flood than sloping areas with permeable surfaces, with water passing through them rocks. Another thing is volcanic activity and volcanoes, such as Jokulholps. Now, these are obviously when ice forms a layer over the top of a volcano and it melts because of the volcano, releasing melt water downstream, down a mountainside, etc. That can also cause flooding naturally. And also, earthquake activity can cause flooding through, for example, the rupturing of a dam or the damaging of a reservoir that releases the water elsewhere. So, human actions and flooding. What is it we do that actually creates the capacity for flooding and actually changes the amount of flooding we can have? So, the thing to remember is that economic growth and population growth since the 20th century has caused floodplains to be built on. We know this even in the UK. There are more and more houses being built near or on floodplains. Changing land use, urbanisation, and house building, etc., all impact flooding, such as these examples: areas of tarmac, wells, sprinkling groundwater onto crops, building dams, channeling streams, ploughing soil, grazing animals, intercepting rainfall in woodlands for use, and deforestation. So all of these are examples of the ways in which we carry out activities that actually increase the likelihood of flooding in an area. And it's also the case that river management, like I mentioned, channeling, for example, and mismanagement has impacted flooding. So hard and soft engineering strategies on rivers impacts flooding. And these may be things such as channelization. Now, channelization is changing the course of a river, and we know that this may improve river discharge and it might reduce some flood risk in some places. But the trouble is, the water is simply moved elsewhere. So it just moves the water somewhere else. It solves the problem in one place, but it creates a problem elsewhere. And therefore, if there's too much discharge in another area, flooding will take place again. Dams. These block the flow of sediment. So what happens is the reservoir essentially gradually fills up with silt, that's sand and materials, and therefore downstream there is an increase in riverbed erosion. And finally, river embankments. So building banks alongside a river. Okay, now they are designed to protect from floods. However, what can happen is they can fail when a flood exceeds their ability, and therefore flooding is on a very large scale when this happens, because essentially the bank is wiped out and all of the water it is containing is no longer contained. Now, these are examples of hard engineering strategies and our interventions. But just to remind you as well that soft engineering can also increase the risk of flooding. For example, greater use of floodplains like we do with building houses. Instead of building houses, we could actually return floodplains to the rivers. Things like that also can increase the risk of flooding by building those houses, etc. It's not allowing the river to take its natural course of flow. It's not allowing flooding to take place in a place that is less dangerous to flood. Now, as part of EQ2, you had to complete a case study on the environmental and socioeconomic impacts of flooding. Okay. Now, you will have applied your own case study as you had a choice here of a few different case studies, but I have chosen to look at the UK summer floods of 2007 and particularly the area of Tewkesbury. So I'm going to quickly run through some of the socioeconomic and environmental impacts in Tewkesbury. The UK summer floods of 2007 were widespread, by the way, so you will find that a lot of the figures you find, depending on where you look at, are similar. And you can just use Tewkesbury as an example if you want to. So in Tewkesbury, there were 13 lives lost and hundreds injured. 50,000 homes were damaged. 850 families evacuated to caravans. 140,000 homes had no water supply because the water treatment works had to be shut down. And that's because in the natural hydrological cycle, the water actually was contaminated and therefore could not be treatable. Total cost to the UK economy of the UK summer floods in total in 2007 was £3.2 billion. Now, when you bear in mind that the UK government puts aside about £1 billion every year for floods, this was 3 times that amount in one single flood event. 9,000 businesses were affected overall, and there were 180,000 insurance claims in Tewkesbury alone in the area. So they're the socioeconomic impact. Now, the environmental impact. River courses were destroyed. Natural river courses, obviously, were tampered with by nature and destroyed. Pollution of rivers and aquifers was widespread, and that's one of the reasons why the water treatment works had to shut down. Debris and foreign objects were deposited on the environment, on roads, in people's gardens, etc. However, soil replenishment is one of the positive impacts of this type of flood. It allows the soil to essentially be renewed by being moved over time. And also, what floodwater does is it completely recharges our groundwater stores and our aquifers. So it completely fills those and becomes a larger store for the future. Now, back to climate change briefly. We need to think about what impact climate change has on precipitation amounts and evaporation amounts as well. So we know that climate change is all about increasing temperatures, global warming. It's about increasing intensity of storms. It's about more unpredictable weather. And that's because it changes precipitation amounts or the inputs in the hydrological cycle itself. And it does this in the following way. The warmer atmosphere holds more water vapor. Impacts such as increasing rainfall intensity, geographical area of precipitation increases in the tropics and decreases above and below the tropics. So what we're saying there is the amount of rainfall that's in the tropics currently will increase, and the amount of rainfall above and below the tropics will decrease. The length and the frequency of heat waves will increase, and actually the length and frequency of storms as well will increase. In other words, less predictable weather, less predictable rainfall amounts, less predictable inputs in general. Now, for evaporation, which is how water comes out of the system into the atmosphere, that also becomes less predictable in most areas. However, what we do know is areas such as Asia and North America are seeing increases in evaporation rates, and transpiration generally increases from plants too. But that has the major impact of soil moisture and soil becoming drier because more water is leaving the landscape and the system. So that impacts the amount of crops and the crop availability there is, and that impacts overall evaporation rates as well. Now, we need to briefly look at the impacts that climate change may have on stores and flows within the hydrological cycle. So let's start with our stores. Climate change is going to create more low flows, and that means droughts. And it's also going to create more high flows, which means floods. So what we're getting is two extremes. Okay, so more low flows, more droughts, and more high flows, more floods in different areas of the world at different times. And we're also going to see an uncertain amount of groundwater flow, because what's going to happen is as we continue to abstract water from the ground, so as humans interfere with groundwater, that leaves an uncertainty in the amount of groundwater flow that will be available, and aquifer availability too. So they're the stores and the climate change impacts on them. Now, in terms of flows, there are four key ones to think about here. So let's think about reservoirs, lakes, and wetlands to start with. We know that temperatures are increasing in the world, and what will happen therefore is wetlands, as we said earlier, will see a decrease in storage and the amount of water that they can store. So there is a decrease in the flow of water through wetlands, through reservoirs and lakes because of higher temperatures. Now, soil moisture is an interesting one. Actually, overall across the globe, it is possible that there is little change in the amount of soil moisture there is. However, it will be two extremes, as I said before. So we will get longer and more periods of drier soil and longer and more periods of wetter soil. So we're changing the balance in the amount of water there is in the soil. In terms of permafrost, which, just a reminder for you, is literally permanent frost in Arctic and tundra regions, what we are likely to see, and what we are already seeing in Alaska, for example, is more melting of that permafrost taking place. And what that does is it creates an even deeper active layer of soil. And we know that permafrost, just like ice, stores methane, stores CO2 already. And what that will do when it melts is it will allow the release of that methane and CO2. So potentially we're going to have a double effect or a multiplier effect here, with more gases being released into the atmosphere, more climate change, more impacts on that permafrost and all of the other flows and stores. And finally, snow and ice storage. What we're likely to see, and what we are seeing already, as we know, is glacial retreat, so glaciers shrinking, and a decrease in snow cover seasons, a decrease in the amount of time of a season that there is snow cover over certain places. So think of the Alps, the Andes, etc. Think of ski resorts in France. The amount of time that they get snow coverage for every year is likely to continue to decrease. We've already seen in previous years, in the last 20 years or so, that some of these resorts, like Chamonix, have had to close at particular times of the year they've never had to close before. Okay, and that is linked to climate change. So snow and ice overall are a decreasing store as a result of climate change. So therefore, what we're saying is climate change causes uncertainty. And there are a number of different ways, and I've already covered some of these, in which it does cause that uncertainty. So let me just round up what ways climate change is causing uncertainty for the hydrological cycle and meteorology. So increases in temperature leads to increases in evaporation. That leads to reservoirs being at threat in summer. And it also leads to potential changes in discharge amounts. We know that greater rates of evapotranspiration means forest stores may weaken. We know that oscillations like ENSO, for example, lead to increasingly unreliable patterns of rainfall, less predictable seasons of rainfall. We're going to get more frequent cyclones and monsoons potentially in India, Asia, and so on. We're going to see increasing intensity and frequency of flooding and droughts because of global warming. We're going to see aquifers and storage of water in underground areas depleted. We're actually going to see decreasing rainfall in some parts of the world because of global warming. And we're going to have a loss of snow and glaciers as a store. And that threatens many communities in mountainous areas like the Himalayas with flooding and other issues. So that's just a summary of the uncertainty and the problems that climate change is causing for the hydrological cycle, for meteorology, and for droughts and flooding. So that is the end of the roundup of EQ2. I hope you found that useful. The next recording of this will look at EQ3. Again, please make sure you listen back to that a few times. Use it as a revision tool. That is what it is there for, and I hope you find it useful overall.